Hey everyone, thank you all for joining. Today we have two great presentations, Derived Column, user-defined function, Derived Column, and Pinot managed real-time to online flows. So I'm Karine, I oversee community at StarTree, and we have two amazing speakers today. I'm gonna bring them in, Neha and Jackie. Hey guys. So we'll be starting off with Jackie's presentation, and afterwards we'll do a Q&A and 5 minutes approximately. Then we'll jump over to Neha's presentation. Then we'll also do another Q&A after Neha's presentation. Of course, if you are watching live, feel free to ask questions directly in the chat on YouTube. And if you happen to be watching this on demand afterwards, you're also welcome to join the Apache Pinot Slack, which will post right in the chat right now. You can join the Apache Pinot Slack where you can see Neha and Jackie. You can ping them directly and do what I do and just send them messages consistently throughout the day. Yeah. All right, so we'll get started. So Neha, I'm gonna put you backstage real quick, and I'm gonna give a quick introduction to Jackie. So if you haven't met Jackie yet, it probably tells me that you haven't been to any of our meetups because he's been presenting pretty much every week consistently. Jackie is a founding engineer at StarTree. Before that, he worked at LinkedIn Pinot team for 4.5 years and became the PMC and one of the top committers for Apache Pinot. His goal is to make Apache Pinot the fastest online analytics platform on the market. All right, Jackie, I'm gonna let you take it away, and we'll see you at the Q&A after your presentation.
Cool, thanks, Karine. Hi, everyone. So yeah, I'm Jackie, and today I'm going to talk about the derived column in Apache Pinot. So before getting into the derived column concept, let's first look at a use case example. So assume I have a table called ads clicks table. So within this table basically tracks the views and clicks for the ads. So here are some example records within the table. So this table contains 4 different columns. The first column is the ads ID, the ID of the ads. And then in this table, we track the number of views and number of clicks for this ads at a given timestamp. And as we can see, the timestamp here has second granularity. And here we simply drop the milliseconds part for this timestamp. Okay, so let's look at some queries. So for example, here for this, for this analytics, I want to know the number of clicks per hour on 2020, basically on today. So here, the challenge here is I don't have this hourly granularity on my timestamp, but I want to track the clicks per hour. So here, what I can do is I can select the sum of clicks, and I can use this toEpochDays function on this timestamp to make it into different granularity. For example, this toEpochDays, I can convert this timestamp from seconds granularity to days. And similarly, for this group by, I can use toEpochHours to get this timestamp bucketed in hours so that I can get the total number of clicks per hour. Okay, let's take another example. For example, I want to know the average conversion rate since July. So the conversion rate basically means the clicks divided by views. Or like how many, basically, I'll just make an example. Like for ads ID 1 at timestamp July 27th, I got 5 views, 3 clicks. So basically, the conversion rate here is 60%. In order to get this average conversion rate, I need to calculate this clicks divided by views, and then do an average aggregation on top of it. So as we can see in these 2 query examples, I need to do something called transform function. What is transform function? So transform function is basically for each record, we can calculate the value based on the value of some columns. So here are the examples shown in the above queries. So these three transformation results, it doesn't exist as a column, but some transformed results. So all these three transform functions are inbuilt transform functions. Besides these functions, Pinot also supports user-defined functions, or UDFs. So currently, Pinot supports Groovy script and also the annotated Java method as the UDFs. Okay, so as we can see in the above examples, it's not possible to achieve that without transform function. So basically, transform functions add great flexibility to Pinot, but also at a cost of worse performance comparing to directly filter or aggregating on columns. For example, for the first query, in order to solve the filter to epoch days, timestamp equals July 27th, I have to scan all the timestamp within each record, and then try to match that value with July 27th. Another problem is because this transformed results does not pre-exist in my dataset, I'm not able to add any indexes to the transformed results. Okay, so now let's think how I can basically optimize this to get better performance. So one idea would be, okay, maybe I can pre-materialize the transformations so that basically these transformed results are already pre-calculated, and then I can directly use it. So the first approach would be, okay, let me pre-process the data before I ingest it into Pinot. So I can probably do a Hadoop or Spark job and then pre-process the data to generate the column. For example, pre-bucket the timestamp into hours and days, and then put a separate column for it. But to run a Hadoop Spark job, I need to take extra resources. And also, I need to maintain extra workflows, which is undesired because basically it's too much effort. Then luckily, within Pinot, we support a feature called ingestion transforms. What it does is, instead of calculating the transform functions at query time, Pinot can pre-materializes the transformation results into a column during data ingestion without a separate data pre-processing job. So to configure ingestion transforms is quite straightforward. So basically, all we need to do is put this transform configs within the ingestion config in the table config. For example, here we can put two separate columns. One is called this timestamp, and basically it's timestamp bucketed in days, and another one is hours TS, which is timestamp bucketed in hours. So with this ingestion transform function columns, actually these pre-materialized columns are physically stored within the segment. So basically, it acts exactly the same as regular columns. And because of that, indexes can also be applied to these columns. For example, we can apply inverted index, sorted index, range index, Bloom filter, and also StarTree index. Okay, so seems the problem is solved, but what if I already have a data set and I already have plenty of segments, data within the table? I don't want to rebootstrap the table with this pre-materialized columns. Here's where the derived column is shining. So basically, the concept of derived column is very simple. It's column with its values calculated from other columns. For example, in the above queries, these three transform functions can be modeled as derived column. And then what's special about derived column is derived column can be generated on the fly when segments are loaded on the server. So what does it mean? So it means, let's say I already have a lot of segments loaded on server side, and then I don't have this derived column yet. In order to generate it, I only need to configure the derived column the same way as the ingestion transforms, like this. And then I update my ingest config within the table config. I add the derived columns into the schema. Then I can simply trigger a table reload. Table reload basically like make the controller send a message to all the Pinot servers to ask them to reload all the segments for a table. During the segment load, the generate derived column will be automatically generated. And then after reload is done, derived columns are ready to be queried without downtime. So actually, this whole process is transparent to the user. Like user even won't be able to find out that the table is in reloading state. So let's take another look at the two examples shown before. So with derived column, in order to get the number of clicks per hour on 2021 July 27th, so the query will look exactly the same as like querying the regular column. So here we can directly use the days timestamp and hours timestamp. Similarly, for the average conversion rate, I can directly do an average on the conversion rate. Okay, so furthermore, the derived column can be paired with the on-the-fly index creation. So basically, we have the following indexes supported with on-the-fly generation: inverted index, range index, Bloom filter, and also the most importantly, StarTree index. So I want to mention StarTree index separately because with StarTree index, actually you can do pre-aggregation on top of the derived column. So for example, for that, for the average conversion rate, for the number of clicks group on per hourly bucket, actually we can apply a StarTree index on the hourly timestamp so that we can pre-aggregate the results for the total number of clicks. So to read more about StarTree index, which is a very powerful index and exclusive in Pinot, please go to our documentation and then find more details there. So with this on-the-fly derived column generation and index creation, to optimize the slow query becomes very easy. So first we can add derived columns. Then we can apply indexes. Both of these two steps can happen within by updating the table config. After updating the table config, simply trigger a table reload. And then you can just sit tight and observe performance boost without downtime. Okay, thanks. So the derived column feature is supported since Pinot release 0.7.1. And that's all about my talk. Any questions?
Thanks, Jackie. So yeah, we do already have some questions. Just putting it out there, if any of the attendees watching, if you have any questions for Jackie, please ask now. We do have a slight delay in the video for when it streams live. So I'm just going to put in here. We do have one question that just came in while you were presenting.
Yeah.
So Yash Sharma said, actually, I think I can bring it onto the screen. In practice, cool. It is cool, right? I haven't used this yet. So I'm really excited about it. In practice, trade-off between derived column and pre-materialization, especially the overhead of index generation and latency.
The overhead of latency. So trade-off between derived column pre-materialization. This is a good question. So basically pre-materialization, let's see. So basically the overhead is on the segment reload happening on the server side. And then pre-materialization basically means we already pay this price as segment creation time. So there's no overhead on the server side. But in reality, I think the overhead is pretty low, and then we haven't run into any problems so far, like with segment derived column generation on the server side. And then we can think of it this way. So it's not possible to do the pre-materialization on existing segments. So the only option would be derived column. Yeah.
Nice.
So basically, yeah, the latency overhead is not very obvious.
Thank you. So if we have any other questions, please ask now. We can also bring you back, Jackie, at the end if people have additional questions while we're doing Q&A after Neha's presentation as well. But that was a really good question.
Yeah.
Cool. Okay, so not to take too much time. We have another question. Excellent feature. Does this feature work on real-time consuming segments, especially if my ingestion is done via my plugin?
Oh, good question. So yeah, for this one, similar to the, we call the feature schema evolution. So the new added columns, basically derived column is also a new added columns. So new added columns won't directly reflect to the consuming segment. So in order to get the derived column generated, we need to wait until the consuming segment is committed. Once it's committed, then the committed segments will have this derived column generated. And then the real-time consuming segment actually support the ingestion transforms. So the next consuming segment will directly do this transformation during the record ingestion. So basically, yeah, you just need to wait for the current consuming segments to be committed.
Cool. We do have two more questions that came in. Jumping. Thanks for the great talk, Jackie. Oh, actually, one other question has already been answered. After I derived columns and trigger the table reloading, can I start to query those new columns immediately or have to wait for the reloading to finish?
Yeah, good question. So we have to wait for the reloading to finish, because before reloading is finished, Pinot doesn't know, or actually, yeah, the column is not physically generated. So basically, the server will drop the segment because the column doesn't exist.
Got it. Cool. Thank you. These are some really good questions. Awesome. So Jackie will be available also after the Q&A. We'll bring him back in just in case anybody has any leftover questions. But you can also join the Apache Pinot Slack where Jackie and Neha are both there. So if you see this after the fact and you still have more questions burning inside of you, feel free to ask in the Apache Pinot Slack. Cool. Thank you, Jackie. This is awesome.
Yeah, thanks, Corey.
And thank you for presenting every week, week after week, of all the cool things that you've been working on. All right, cool. So I'm going to put you backstage and then I'll bring Neha out. So really quick before I bring Neha out, I'm just going to give her a little introduction. So Neha is a founding engineer at StarTree. She's also an Apache Pinot PMC and committer. Prior to her current role as a founding engineer at StarTree, she worked at LinkedIn as a senior software engineer in the data analytics infrastructure organization. Neha is Apache Pinot PMC and committer and has made numerous impactful contributions to the Apache Pinot project. She actively fosters the growing Apache Pinot community and loves to evangelize Apache Pinot in the form of blogs, video tutorials, speaking in meetups, and conferences. You can also find her on Twitter at Neha Pawar 18. So Neha, welcome.
Hey.
Hi. Cool. So I'm just gonna back out and let you take it from here, if that's okay with you.
Mm-hmm.
All right. I'll see you afterwards for the Q&A.
Awesome. And thanks for the great intro, by the way. So welcome to my talk, everyone. This is Pinot Managed Real-Time to Offline Flows, also sometimes known as the real-time to offline job, or you can also think of it as how to offload your real-time table operations to Pinot so that you can go and take a vacation. So before we jump into what this feature is and how it works, I'm going to spend some time talking about why we built this. And to understand that, we are going to take a look at the differences between a real-time table and an offline table and see how those differences create some complexities and overheads in the management and operations of a real-time table. So a quick recap on the Pinot architecture. So if you've already been attending these meetups and are familiar with Pinot, this might already seem familiar to you. So we have the first component is the Pinot servers. Pinot servers are what hold the Pinot data in the form of Pinot segments, and then they serve queries of the data that they have. And then we have the Pinot brokers that accept queries from the users, which they forward to the servers. They get the results back from the servers, which they merge and send back to the callers. And finally, we have the Pinot controller, which manages all the components of the cluster with the help of Helix for cluster management and Zookeeper as a metadata store. So we see two types of servers here, the offline and the real time. So let's double click into what each of these servers are responsible for. Starting with offline. So typically, if you have some data at rest lying in some file system, like say Hadoop or S3 or somewhere locally, you would be creating an offline server. You would be creating an offline table, and the servers that you use in this case would be called the offline servers. And to get this data into your offline table, you would typically write a batch ingestion job using Spark or MapReduce, and you would process this data one bucket at a time. These buckets are usually like an hour's worth of data or a day's worth of data. Your batch ingestion job would then generate a Pinot segment, and then it will push it into the segment store. And then the offline server pretty much has to just download this segment from the segment store and start serving the queries. So the responsibilities of an offline server are download a ready-made Pinot segment, start serving queries. That's it. And because we use these ingestion jobs and process the data one time window at a time, this naturally helps us create segments, Pinot segments that are aligned to the natural time boundary. So why is this advantageous? Because there are certain operations that rely on knowing this time boundary, rely on these segments being aligned to the time boundary. So for example, if you wanted to do a backfill, now let's say you had data for 3 days, 14th, 15th, and 16th, and you ran 3 ingestion jobs, and each of them generated one segment called 14, 15, and 16. And now if you wanted to backfill just the data for 15th, and you had that data lying around somewhere and you created a new Pinot segment, it would be pretty easy to just replace the segment number 15 with your new segment. And then there's also, because we have these ingestion jobs, this is kind of giving us a chance to perform other data processing operations, such as doing any roll-ups for a particular time range, or let's say you wanted to dedupe the data for all the events that you have in a day, or let's say you wanted to round your time granularity to something coarser. So these offline jobs give you a chance to do all those operations. Now let's take a look at real-time tables. So if you had data in a real-time data stream, you would be creating a real-time table, and the servers in this case would be called real-time servers. So real-time servers have their life is much harder compared to offline servers. They don't have it that easy. So they are doing a whole bunch of things. So the real-time servers are directly ingesting events from the stream. They are indexing those events as they consume them. This indexed data is kept in memory. They are also serving queries of this in-memory data that they have. And then periodically, all the in-memory data gets converted to a Pinot segment on the real-time server. And then the server has to push this segment to the segment store. And it also retains a copy on the server to continue serving queries of that data. So as you can see, there's a whole bunch of additional responsibilities, and these add additional memory overhead on the real-time servers, especially the keeping index data in memory and building the Pinot segment using the in-memory data. And all servers are doing these activities for typically several partitions at a time. So let's consider this example where we have a data stream that has 4 partitions. And you can see that the consuming segments and the completed segments have pretty much spread across all the pool of available servers. So because of these additional responsibilities and these variables that are present on the real-time servers and all this additional memory overhead, the capacity provisioning and tuning and management of real-time tables tends to be relatively complex compared to an offline table. Also, in real-time tables, it is not possible to create segments that are aligned to the natural time boundaries the way we were able to in the offline table. And let's take a look at why that is the case. So let's bring back our stream that has the 4 partitions. Let's say this represents the data in the partitions of our stream. So going from right to left, we have data starting from 14th of July, and then 15th and 16th, all the way up to 17th, which let's assume that is the present day. Now, suppose a real-time server started consuming the events of the pink partition. How does the real-time table know when to stop consuming and when it should be building the Pinot segment to flush onto the disk? So this segment completion is triggered on thresholds. And these thresholds are something like the number of rows consumed or the number of hours consumed. So it's not really possible to create segments which are aligned to the natural time boundaries. So typically in your partitions, the segments that get generated would look something like this, where they span across the time boundaries and will have arbitrary start and end times. By arbitrary, I just mean that you won't typically have a segment that starts on 14th midnight and ends on 15th midnight, or segments that are like 1 per hour. You won't have something like that. Same thing for all the partitions. And another thing to note is that the segment boundaries, they don't even match across the partitions. It's like totally random. So why is this a problem? Because we saw earlier that there's certain operations that rely on having segments aligned to time boundaries. So in real-time tables, it's not possible to easily do a backfill on a specific time range, or if you wanted to do roll-ups for a particular time range, or dedupe the events across, like say an hour or a day, that's again not possible. And also we spoke about the segment completion thresholds, right? Like number of hours and number of rows. If you do not get the tuning of that right, you can end up with problems like creating too many segments or creating very small segments. Or if you have too many partitions in your stream, then again, you're going to end up with a lot of segments. And these problems will directly impact the performance of your query in the cluster. Okay, so to summarize, we saw that real-time tables and real-time servers in particular do a lot more activities compared to the offline server. And so the management and capacity provisioning and tuning of real-time tables tends to be relatively complex compared to the offline table. And also certain operations like backfill, roll-ups, dedupes is not easily possible to do in real-time tables. So what does this mean for you and your real-time table? So what if you do have a long retention real-time only table, and or you need the ability to backfill a particular time range in your table, and you want to be able to do roll-ups and dedupes as your data gets older. So typically in such a scenario, we would recommend that you set up a hybrid table. In hybrid table, you would create a real-time table and an offline table with the same name. Your real-time table would have like very low retention. So let's say like a few days, 2 days or 5 days. And then your offline table can have as much retention as you want. And your real-time table will continue to consume. You will set up the ingestion just like it was before. And then you just have some additional steps. And those additional steps are, you would have to set up some ETL to get all your real-time events onto, say, a remote FS like S3, Azure, Hadoop. And then you will have to set up ingestion jobs to periodically read data from your remote FS, create the Pinot segments, and then upload them to your offline table. And while real-time tables work great, there is one major issue with this approach that we just talked about. And that issue is that this is so many additional steps for someone who just wanted to ingest events from their real-time table. So a user is saying that, hey, all I wanted to do was ingest events from the real-time stream, put it into a real-time table. And are you telling me that now I have to write ingestion jobs? I have to manage those ingestion flows. So what if like I don't want to do all this? Like I just want the simplicity of consuming from a real-time stream. So this is where Pinot managed real-time to offline flows will come into the picture. With Pinot managed real-time to offline flows, as the name suggests, data will be moved from the real-time table to the offline table automatically. You don't have to do anything. You don't have to write your own ingestion jobs and maintain those jobs. Pinot will do it for you. And this movement of data happens one run at a time, where each run is like one time window. So this is kind of simulating the behavior of how an ingestion flow would have done it. And while moving data from the real-time to offline, the segments also get aligned to the time boundary. This helps us eliminate most of the problems that we talked about, which arose with having misaligned segments. This also gives us a chance to apply any processing as needed to the data when it moves to offline. So this is your chance to apply rollups, dedupes, time rounding, and so on. So let's dive deep now into how this exactly works. Let's bring back our data stream from before with the 4 partitions and the data in the partitions from 14th, 15th, 16th to the present day. And we also see the Pinot segments that have been created for each partition. And towards the end, we see the consuming segments for each partition. So Pinot table is actively ingesting data from the stream and also has created some segments in the real-time table. Okay, so in the previous slide, we said that Pinot managed flows is going to move the data from the real-time table to the offline table, one window at a time. So one run at a time, and each run is going to be one time window. So our first step is going to be to calculate the time window. To do that, every time we are going to try and find the oldest day, the earliest day that has not yet been moved from the real-time table to the offline table. So in this case, for cold start, that earliest window is going to be the 14th of July. So our first available time window is going to be start of 14th to the end of 14th. Our next step is to select all the segments that overlap with this time window. So in this case, in this example, that's going to be these 4 segments that are marked here. And we see that these segments are kind of spilling out of the desired time window for us, but that's okay. We're going to take care of that in the next step. So in the next step, we take all these selected segments and then we do data processing and segment generation. So in this step, we will filter out the portions of the data that we don't care about, the ones that don't fall in our time window. And with the remaining data, we will create a new segment. So this segment will now have data only for the 14th. And then this segment will be uploaded to the offline table. Let's take a look at the second run. So the next available time window is going to be the 15th of July. Next step is to select all the segments that overlap with our time window. So those segments are the ones marked in this slide. And finally, we will process those segments. So filter out the portions we don't care about, create the new segment for 15th of July, and then upload it to the offline table. To do this processing of the segments, filtering out, etc., we use a segment processor framework that is also part of Pinot. This is a very generic and flexible framework that lets you convert M segments to N segments. This also gives you a chance to apply some processing to your data. For example, partitioning, filter, sort. So typically, if you had set partition, filter, or sort in your real-time table, this framework is going to be able to honor those same configs while creating segments for your offline table. This also gives us a chance to do those aggregations and roll-ups and all those operations that we said that we could not have done previously in the real-time table. So you can apply any dedupes, or you can convert your time column to a coarser granularity. You can roll up and merge the rows if you want. And finally, when it builds the segments, it's going to use the same indexing config that you had applied to the real-time table. And your offline table segments will have the same indexes generated. Now, just for fun, let's take a look at one more run of how this is going to happen. So our next time window is the 16th of July. But as you can see from the blue partition, we do not have the complete data for 16th flushed onto the disk as of yet. So the segment _1_5, that's still a consuming segment, and it contains some data for the 16th of July. And because of that, at this time window is going to be skipped. The next time this job again runs, it's going to try and process the same time window. So this helps us ensure that we do not prematurely build segments for the offline, and we will only proceed with the next runs after we are able to successfully get all events for 16th and then keep going ahead one day at a time. Cool. So far we saw how this works conceptually. How do you enable this if you want to use this in your setup? To do that, you would simply put this config in your real-time table. This config is telling your table that enable the real-time to offline segments task. This is a very bare minimum basic config, but there's a whole bunch of other configs that you can put inside this map if you wanted to more closely control the behavior of how this is working. So you have a bucket time period. This is by default 1 day. This lets you control the size of the time window that you operate on. So in our example, we were doing the movement 1 day at a time. So that was because the bucket was 1 day. But you can set this to anything you want, like 1 hour, 2 hours, or anything. Then you have buffer time period. Again, the default value is 2 days. And this simply means that the time window will not be processed unless it is older than the buffer time period. Then you have the merge type. So this is where things start getting interesting. With the merge type, this lets you set like a function so that you can merge and compact your rows and reduce the size of your data. So there are 3 types. You have concat, dedupe, or rollup. So if you set it to concat, there's going to be no merge. It's simply going to just concat all the rows. If you set it to dedupe, it lets you dedupe your rows across the window that it is processing. So if 2 rows are seen that have the exact same values across all the columns, they will be counted as only 1 row. And then finally, you have the roll up. So with rollup, if the same values are seen across all the dimensions that you have, they will be merged into one row and the metrics will be summed up. And instead of summing up the metrics, you can also change the aggregation type to max or min using the next config here. So in this example, we're saying that roll up the rows, but when you will merge the metrics, use the max aggregation function. And then you have the round bucket config. This lets you define how you want to change the granularity of your time column. So typically you have milliseconds in your real-time stream, but when you are pushing it to the offline or as your data gets older, you're okay with having just data rounded off to the closest hour. So this is the config that will help you with that. And finally, a config that lets you control the maximum number of rows that you want in your offline segment. Okay, so far we conceptually saw how this is working. We saw the config that you would enable to start using this feature. Now, who is orchestrating all this? Who is making all this elaborate set of steps happen across the cluster? And the answer is the Pinot controller with the help of the Helix task framework and also a new component called the Pinot minions. So let's take a look at how this is happening. Bringing back our cluster diagram from before, I've added the new components here, the Pinot minions, and also the task queue. The task queue is part of the Helix task framework. Now, let's say you created your real-time table and you added this config to enable this movement feature. The Pinot controller is running a periodic task in the background. And every time it runs, it looks for tables that have this config enabled. And now when it finds table underscore realtime with this config, it's going to perform the first two steps that we discussed earlier. So the first step would be to calculate the time window that it should operate on. And the second step would be to select the segments that fall in this time window. And using this data, it's going to create a task spec. So the task name is real time to offline, the table name, the segments that were selected, the window start and window end. This task spec will be put into the task queue, and a minion that is free is going to pick up this task. Then the minion would download the segments, do the processing, create the new segments, and upload the segment to the offline table. Finally, the minion is going to update a special Z node in Zookeeper, which is called watermark. The minion will set the value for this table as the end time of the window that it just processed. So that way, when the controller will wake up for its next run of the periodic task, it's going to look at this watermark, and that's how it will know how to calculate the next time window for the run. Cool. So we are almost at the end of our talk. We saw how everything works. We saw how everything works in the cluster. We looked at the config that you would set to enable this. And just to wrap things up, would like to just conclude with saying that we were able to successfully convert our real-time table to a hybrid table using Pinot managed real-time to offline flows. And with that, we were able to solve our problems of backfill and the ability to roll up and dedupe. And now because we have the offline table, our operations are going to get a little bit easier. And we did not even have to write our own offline flows to achieve all this. And before I sign off, I know this talk was a little dense in content, so would like to leave you with some resources. We have a documentation for this feature on our docs, Pinot Apache org. Please try this at home and let us know how it goes. We are here to answer any questions if you have. Join our Slack channel. We recently hit a milestone in the number of members in our Slack channel, so we'd love to see you there as well. You can also connect with us on Twitter at Apache Pinot. And that's it from me. Thanks.
Yeah, that's awesome. Great presentation.
Thank you.
That was very dense. It was a very dense topic. I love your illustration that you did. That's like, I think it might be my favorite one. Can you go back a slide? Yeah, that's a really fun illustration.
Thank you.
Okay, so I'll put this, I'll put the slide backstage, and then we do have a couple questions that came in. If anybody has any additional questions for Neha or for Jackie, please ask now. All right, so first one that came in, and some of these might have been answered or whatever throughout the thing, but I'll still put it in here. Do we miss out on the real-time aspect of data while we move from real-time to offline ingestion?
Right. So we do not, because even though we are moving from real-time to offline, we are still keeping the hybrid table, right? So we are still keeping, let's say, the very recent data in the real-time table. And then we're only moving, like typically you would set 5 days retention for real-time and then say 2 years for your offline. So you're still getting the real-time ingestion and the instant freshness SLAs that you wanted with your real-time table. You're not losing on any of that.
Cool. Mayank, if I have a different indexing, partitioning, sorting configs for offline versus real-time table, for the segments that are moved to offline, which config applies? He gave a, for example, I may choose not to use StarTree indexing for real-time, but may want it for offline.
Right. This is a good question, but it's a very implementation specific detailed question. I don't remember. I thought it was that we apply exactly what it is on the real time.
I can answer. So sorry for jumping. So yeah, so basically when you move segments from real time to offline, when you generate the segment, it will take the offline config. So basically, yeah, you can change your index type. For example, on real time, because Kafka will use low-level consumer, so it enforces you to partition. But on offline side, you might want to drop the partitioning. So basically, yeah, it's quite flexible. You can basically it takes the config from offline table.
Yeah, that's what I figured, that we would typically honor what is set in the offline config. Just been a really long while since this feature was implemented.
Okay. Istvan asks, does segment processing framework have a Python API or only Java API?
It is only Java.
Okay, so Mayank, he answered that. He was just like, might well for Neha to answer, but there is a question that came in here that I think was answered, but I'm just going to highlight it just to showcase it. And if you guys have any other questions. So I guess we can't do dedup and roll up in one config, since there's no way for us to figure out which events to dedupe and which ones to roll up. And then, oops. Currently we support merge code, concat, rollup, dedupe. These modes are mutually exclusive. If there's anything else that you guys want to add to that, or
was this the question and was Mayank's statement the answer? I'm a little confused.
I think Mayank's question was.
Oh no, this is Jackie. Sorry.
Yeah, sorry. Yeah, I'm answering that question. Yeah, so Mank's question is, can we do dedupe plus roll up at the same time? Yeah, and basically the answer is no, because they are mutually exclusive.
I mean, concat is, but we should be able to support roll up and dedupe together, right? I think that's valid.
I mean, roll up, dedupe, you can configure it in a way, like, for example, if you do max aggregation, then you can achieve the same same behavior.
Got it. Yeah. Okay. Xiaobing says, thanks for the great talk, Neha, and nice doodle. Does this functionality assume the out-of-order data to be bounded?
Yeah, good question. So that's why we had the config for the buffer time period. So like, again, it's like a best guess. So if you think that you may have out of order data coming in for the next 2 days, then you can set the buffer time as 2 days. But if something comes beyond that, then we have lost it. So yes, it does assume the out of order data to be bounded, but you can change it with your config as per your use case.
Got it. And then Xiaobing asked also, curious what happens if some very old data flows into real-time table, like days after the run for their time window was finished.
Mm-hmm. Yeah, again, same problem. I think this is related to your previous question.
Yeah.
If it goes beyond the buffer time, we're not going to move it. But this is what typically happens even if you were to set your own offline ingestion flows, right? Like if your offline ingestion has already happened and you've moved on, and then after the ETL, let's say your new events appear in your real-time stream, you are on your own. You're going to have to go and backfill it separately.
Okay, Kishore makes a statement. Dedupe happens on a specific key and rollup happens on a bunch of columns. So it is possible to do a dedupe plus rollup, but not a rollup plus dedupe. So order matters. Okay.
Yeah, this is similar to what we were discussing.
Got it. Okay. Cool. So I think that if there's no other questions, then I think we might be able to wrap up. Like I said, if anybody has any additional questions, and if you happen to be not watching this live, you can join the Apache Pinot Slack channel, and you can ping Neha and Jackie there directly, or you can just ask in the general or troubleshooting channels. We got some good comments here. Rohit, great talk, Neha and Jackie. Nice t-shirt, Jackie. Awesome. Cool. Yeah, this is really good. So thank you guys so much for taking the time. Really.
Yeah, thank you for organizing this and having us. At least I'm a first timer, but Jackie's now a veteran.
He is definitely a veteran.
It's fun for me.
I'm actually pretty sure that Jackie has done StreamYard more than I've hosted any of the meetups, and I'm here pretty much consistently because there was one that I missed last week. So I think he's more seasoned than I am, and we were the ones who set it up. All right, cool. Well, thank you everyone for joining. Jackie, Neha, thank you so much for taking the time to present. And we will see you next week, hopefully for the next meetup. And don't forget to subscribe, comment, and like. And then next week's meetup is Apache Pinot and Superset forecasting and visualization. So we're looking forward to seeing that. So thank you guys so much. See y'all next week.
Bye.
Bye.